that people do is to control barrier functions or control Lyapunov functions to make sure that the spacecraft behaves the way it should behave. So using those, I'll explain to you what those are, and then using this, we can have docking trajectories or landing trajectories.
Oh, sorry, Devashish, can you please
A little bit
go
of
to
chance here. Please excuse me. I know that you have been looking at very nice pictures of the whole thing.
hello?
I'm going to show you some nice equations, so please bear with me. So usually, control theorists will model the system using an equation of that sort, that is x dot equals fx plus gx and u. X is the state that represents everything that this is you want the system to represent, and u is the control there. Now there is this standard theory called control Lyapunov function theory, in which you define a Lyapunov function. So this Lyapunov function is kind of a yes. Yeah. Okay. Sorry again. Control theory, the equations work very well, but in practice, you need to do a little more than that. So anyway, so we have the system, and then the Lyapunov function, usually it's a quadratic function. Anyway, it's something that looks like your soup bowl, and you want to make sure that your system remains within this. Not only it remains within this, but it also converges to a point there. That is the 0 point that you want to converge to. So what you have is this trajectory in the state space that converges there, and what you see below is a projection of the state onto whatever interest, whatever plane you are interested in a lower dimension. However, using this, you can get a function that will drive you to this point. But when we talk about safety, so this is essentially Lyapunov stability. But when you talk about safety, you are not really interested in driving something somewhere, but you want to keep your system, that is the state, within a certain area or within a certain volume in the state space. For example, let's say that I define a constraint hx is greater than 0. Conventionally, people also say hx less than 0, but we will use this. So that gives rise to a function like this, and you want to make sure that the state remains within that. So that is what we do. So C is actually the set within which you want the state to be, and del C is the boundary. The difference between this and that is that the control that you get out of this will keep the state inside this set, the same set, but it does not try to drive it anywhere. The only thing that it does is that it does not allow the system to go out of the set. So you can go to the boundary and then come back, but as long as it is inside, it is fine. But if it reaches the boundary, it gets pushed back in. So that's the idea. The system pushes back into the safe set. So that idea is now extended to something called a class case function or a class kappa function, which is defined as a mapping alpha from hx which is defined on the interval minus b to a, that is from a negative to a positive value, to a subset of an interval which stretches from minus a. Here is an example that you see that the mapping is 1-to-1 within the same interval set. So minus 5 to 10 is mapped to minus 5 to 10. It's a linear one. It could be a non-linear one. It doesn't matter, right? But important thing is to look at this equation that as long as it is in C, the H dot is actually minus A time alpha Hx. So choice of A will tell you with what force are you pushing the thing inside. What happens here is that as long as you are on the inside the thing, there is everything is fine. But the moment you come to the boundary, then this becomes zero. So this alpha Hx becomes equal to zero. That is why it's called a zeroing barrier function. So the difference between what you see here and what you saw earlier is that the system can remain at the boundary. It doesn't have to be pushed back. Staying at the boundary is fine because you are worried about safety. You're not worried about getting stability or pushing. Of course, stability is a part of it, but you're not trying to push it into some point. But as long as it is there, and you will see that this staying at the boundary is a very important property when you look at a proper, I mean, a realistic problem in spacecraft landing or docking. In contrast, the traditional barrier function that we use is called the reciprocal barrier function, which, if you look at this plot, you will see that when it comes to the boundary, the value of the VHX becomes infinity. So the difference between this and that is that the at boundary this is zero and there it is infinity. So infinity means it gets pushed back into the cell. But we want to use the boundary effectively, so this is a much better idea. So imagine that you have a nominal control for stability, and then you pass through what is known as a safety critical filtering, and then that control goes into the system and there is a feedback loop. So you would like to see what is the minimum variations over the nominal control that you can do in order to achieve what you want to get. So imagine that you are trying to get from point A to point B and there is an obstacle in between. So what is the minimum deviation that you can do so that you can get to the point B and still achieve your destination without changing your control too much? What is too much? This is used by giving, I mean, this is done by using a quadratic norm like this. So use squares kind of thing. The minimum deviation that you have in U will ensure that you have obeyed all the constraints. So this is the safety guarantee that on system dynamics that you are doing, and the quadratic of linear constraints will be there. So we can write it. So let's look at a spacecraft docking problem. So this is the docking port. This is the target spacecraft. That is the chaser spacecraft. The chaser spacecraft has to dock there. So docking points are there. Those two are the docking points. So, however, you can see that both the spacecraft have protrusions from their vehicles, so you don't want them to hit each other. So this is something that you want to avoid, right? And this is how you want the approach. So you want to avoid the orange part and you have to approach through the green part. Now, if you look at a standard trajectory, this trajectory will go like this. I mean, if you just solve a problem without the constraints, then that is not safe. Two things. One is it is entering the forbidden region. The second thing is that it is not coming to the docking port. What is desired is this one. A safe trajectory that avoids this as well as it approaches through the region of approach. So this is the objective that avoids the unsafe region and then approach through the regular pool. So to get that, we define, I mean, this is just one thing, it could be something else as well. You define what is known as a cardioid set. This cardioid set is basically parameterized by A. So if you have different A's, you get different values for the cardioid set. So A equal to 2, you get the outer boundary. A equal to 1, you get the red one. A equal to 0.5, you get the blue one. So imagine that the target aircraft is right here, then you have to avoid this outer boundary. The thing is that what you did here is to represent the forbidden region using an analytical equation like that. That helps because we can now solve the problem by doing the standard procedure that we have laid out here. And what do we get? We have the safe set there, and then we enforce the control value function there, h1x like this. And so we have this u star as a quadratic norm and the subject with the linear norm as given here. So this linear norm essentially, the linear condition essentially ensures that you stay outside of that cardioid pattern. So here are some simulations of that. So you see now that these are the various initial conditions from which the spacecraft is approaching, and it could go through the boundary like this. Irrespective of where it is, it comes, goes to the cardioid pattern, boundary of the cardioid pattern, and then follows that boundary. So this is where the boundary idea comes into play. Now let us see that suppose the spacecraft which is trying to approach, there is an astronaut sitting inside. The docking has to be done with the help of that astronaut who has to have the code within its visual range. If that happens, then you can see that not all these trajectories are useful. So here is the useful thing. So you see the field of view. So the idea is that as the spacecraft approaches the target spacecraft, the field of view should be such that it should always be looking at the docking port, which means that the astronaut sitting there must be able to see the docking port where the spacecraft is going and accordingly make the fine adjustment so that the docking is successful. So this is the additional constraint that we have in the docking keys. There are several others. This is just an example of one such docking thing. So we are putting this constraint as a part of the whole thing. So it avoids this plus it makes sure that the field of view remains within this. So this formulation is possible in the given formulation. Similarly, let's say that you are trying to land a spacecraft on a planetary surface. You can see a planetary surface can be rather rough, and we must have a proper identification of a place where the spacecraft can land. It cannot land just anywhere. So it has an option of say landing here or say landing here. Which one would it choose and how? So these are the standard equations. So we need the objective is to find the thrust profile. So the lander lands at a predetermined landing location within a orbit. It must have a touchdown velocity. It must avoid known hazards when it is trying to land, and it also honors human physiological limits. So look at this. There are two models. One is a flat mesa-like structure, and the other is a triangular structure. So in this case, it can try to land on the top of that trapezoidal shape. Here, it has to completely avoid it and land somewhere else. So for that, now we define the barrier function. This is actually a composite barrier function, not the cardioid pattern that had only one equation, but it has a composite one. It gives you on this side like this and on that side. So left and right, there are two different functions. So left boundary defined by kpx and the right boundary is given by kax. And the lightning point is at that point. So with this also, you can now modify your nominal control so that it remains within the barrier function. So these are one of the functions that we have used to do this. There could be others also. So I will hit the equation. This tells you how to implement those equations that we have given there. And of course, the Lyapunov analysis guarantees that you avoid hazards in the sense that you stay within the barrier. So now look at this. Suppose you want to land at this point, this left-hand point here, then it has the barrier the trajectory has to go like this and then land here, and it avoids the hazard at this point. So a projection on the XZ plane is there, and the projection on the YZ plane you can see there. So this is the way the trajectory has to be. So there are multiple trajectories that can achieve this while avoiding the two hazards on both sides. So it achieves pinpoint landing, soft touchdown, and hazard avoidance. However, when you have an astronaut sitting inside, then just this is not enough. So let's look at a spacecraft, a lander spacecraft like this. It has a body axis attached to it. And look at a astronaut who is sitting inside. Now, if you define the axis on the astronaut's body, then you have the up, down, front and back, and left and right. So the front and back is AX, left and right is AY, and the up and down is AZ. Now, human physiology is such that you can tolerate more stress in the frontal direction than in the up and down direction, and the least in the left and right direction. So there are standard tolerance levels that are defined for this. This is in the NASA space standard. I'm sure you must know about that. I imagine that the astronaut is sitting inside, and each body frame is given by AX, AY, and AZ. These are the tolerance levels that are given for emergency cases and standard cases where there is a non-deconditioned flu and a deconditioned flu. So different levels are there, and there the lower and upper limits on the acceleration are plotted. So this is given only for the AX part of it, that is the frontal part of it. That is what is the lower limit and what is the upper limit on. So now let us look at our landing trajectories here. Now, in that figure, if you look at just the rightmost barrier, what it gives rise to is the leftmost barrier here. So let me, I don't think there's a pointer here, but if you look at the green line there, that corresponds to the rightmost barrier, and then you have the next one, and then the next one. So the barriers in the trajectory here are different because they are approaching like this, through this. So essentially, how you choose the barrier will tell you what the trajectory would be. Now, suppose I analyze those three reference trajectories here, you will see that this barrier you got for K1 for 1, K1 12.5, K1 equal to 50. And you can see the most vulnerable part of the human body, that is the axis which is left and right. You can see that when you use K1 equal to 1, it actually crosses the tolerance limit for the human being. The AY tolerance limit it crosses there. Whereas if you use K1 equal to 50 or K1 equal to 12.5, it stays within the limit there. So the choice of the barrier function depends on can be dependent on the physiological tolerance of the astronaut. So 12.5, among these 12.5 appears to be the best. As you can see, it is the lowest from the limit. Another example where you have a choice of two landing strategies. There you had only one landing point and three different barriers. Now you have two landing points, and which one do you choose? You can do a similar analysis here as well. And you have this right barrier and left barrier for both the points. And then you get these results. So if you look at this, you will find that the landing at A will give you a better value than landing at B, which touches the limit on the left side. So you which means that you would like to land at E rather than at B. So this selection of the landing point and hazard avoidance based on human physiological limit is also can be taken into account in the formulation of the problem. So these are some of the references that we have, which that we use for this. And with this, thank you. This picture is very important because this is the crater that the Chandrayaan-3 rover encountered on August 27, 2023, as seen by the navigation camera. So essentially, if you wish to avoid this crater, you have to choose a landing point which is different from this. Thank you. Any further?
Sir, I've seen spacecrafts